Thanks so much, Benjamin. It was great to see your talk, and it was humorous. I think you all agree. Just want to remind you that there is a reception after this talk. Stick around. I think it's out on the patio. I can get you more details right after this. So I'd love to introduce Oscar from LinkedIn. He's going to talk about porting iOS apps to Bazel. Oscar?
I guess this is a clicker. Hello. Yeah, feel free to leave. Don't feel guilty. This is the last talk of the day, so no worries. Long day. Actually had two separate nightmares last night about this talk. In one, the whole auditorium was empty, and Dimitri just told me, you know what, we can just skip it. And I was like, yeah, I'm fine with that. So thank you to the people remaining. The other one was the Leaf guys giving the exact same talk that I had prepared. And I was like, well, here we go again. But unfortunately, I'm not really, I know the talk is porting iOS apps to Bazel, but this is more like the path we took to port our iOS app to Bazel. So I apologize for that. I have a knack for coming up with witty titles and then not following through during the talk with the wit of the talk's title. So this is going to be like a longer version of a talk that I did that was called Sweat, Tears, and Desperation, porting our app, or something like that. So I'm essentially going to talk about 4 different things. One, the iOS apps we have at LinkedIn and how we used to build them. That's the second part, actually, the before Bazel part. And then I'm going to talk about our migration and what it involved and how we accomplished that and where we are right now. And I'm going to try to make it quick so we can all go at the reception and be done with this. So at LinkedIn, we have 7 apps in the App Store, and we have around more than 100 iOS developers that produce more than 100 commits per day. Of those 7 apps, there is one app, the main LinkedIn app, that is orders of magnitude bigger than the next biggest app. So we have a ton of libraries and frameworks, hundreds of them, that we need to support. So we have this, there's a bunch of little guys, but there's like one huge guy, and we need to support both of them. And that can be quite challenging. The build technologies that we used to use, we still use some of this, most of them, actually all of them. And in 2018, we basically had this pipeline where we were running something we call multi-product, which is a fancy way of saying we have a bunch of different Git repos, so it's essentially a multi-repo. And each one of these Git repos has some metadata associated with it. It has essentially a JSON file. And then our CI pipeline knows what to do with these repos based on information on that JSON file. It knows where they go, where they get deployed. Are you a service? Do you need to go to a data center? Are you an app? Do you go to the App Store? Maybe you're an Android app. You have to go to the Play Store. Maybe you're a command line tool. You have to go to something that puts you in all developers and production laptops or whatever, right? And so that's technology that we call multi-product. We, as a build system, went crazy with Gradle. It solved the problem we had with Maven. And then we said everything should be Gradle, so we went way above and beyond what we should have done with Gradle. But and then for the last 2 are specific to iOS apps. One is a dependency management system that iOS developers are probably familiar with. It's called CocoaPods, and it essentially does dependency resolution. And then last but not least, Xcode, which is the thing that actually builds the product. And as Keith was saying from Lyft, it's a black box. There's a command line tool called Xcode build, we call it, and then there's an app that pops up in the other side, and hopefully nothing goes wrong. And if it goes wrong, our only recourse is file a bug with Apple maybe, or rerun it, hope that it works the second time. It's a fine thing to do. That's roughly our CI pipeline. It has not changed with Bazel, so I just wanted to give you an idea of what it looks like. We have this process where developers will write code, and then they will commit, and we run a bunch of tests before merging. We essentially build and test the entire app in a pre-merge step, and then we merge it with trunk or master, however you want to call it, depending which SCM you use first. And then we run everything again. So we essentially run everything twice. Those are release and debug builds. The release build is ARM v8, ARM64. The debug build is x86-64. I got confused. The release and debug builds are both ARM. One has debug symbols, and the other one is optimized. So we split them up, and then we run 4 separate, all the squares are machines, by the way. So we run 4 separate machines, and each machine runs 12 simulators using something we built called BluePill, which is a tool for running parallel simulators. And so we run a bunch of tests. And back in 2018, we had a bunch of problems with this architecture, but the biggest ones were the builds were pretty slow. It was taking close to an hour for one of those runs. So if you committed code, and from the time we have some metric that is called commit to publish, it's from when you commit to when you actually see the end product published, obviously. And that metric was about 2 hours because we run it twice. So if it takes 1 hour, then we run it twice. It's 2 hours. And then we were trying to fix the slow builds. The other problem is that when there were problems in the pipeline, debugging those problems was really hard. All you ended up with was a log. We didn't really know we had built some tooling that will like parse the logs and try to divine what went wrong, but that was pretty fragile. And we also had some problems where when some tools that Apple provides, will fail, our only recourse was rerun the whole thing, and then Xcode will not necessarily work well incrementally, so it take a while again, and it never gave you that warm fuzzy feeling that you knew what you were doing. It was like a big hammer. So those were the problems that we were trying to solve. And we considered a bunch of solutions. We did extensive analysis of, what can we do? Can we buy faster hardware? And the answer was no. Apple doesn't sell any faster hardware. This was 2018, so it was before they announced the Mac Minis. We tried to do binary frameworks, but we have a bunch of Swift. We were one of Swift's early adopters, and Swift does not have binary compatibility, so it was pretty sketchy. We thought about throwing more machines at the problem and splitting them up in more, but we had a few problems with that. One was that the longest pole was the release build, and that was not really easily parallelizable across machines. And the other one was that the more machines you throw at it, the more you are susceptible to one of them failing for an unrelated infrastructure issue. And nothing makes developers more angry than when their things failed not for their own fault. I guess they also get angry when it's their own fault, but they get more angry get angrier when it's somebody else's fault. We thought about working in the compiler, but then we realized we didn't have any compiler people, so that meant like ramping up a new team and investing in trying to fix Swift. We looked at the work that Apple was doing with Swift, and we were like, well, that's a hard problem. We probably can find something easier. And then we landed with changing the build system. That looks easy, right? So we went and looked around for a bunch of different build systems, and we looked at the entire landscape, even crazy, like, why don't we just use GNU Make and like chuck Ccache in there, and maybe that'll work. But after taking a sample app, a small app, and doing a bunch of iterations, building it with different build systems to get a feeling for what it looked like and how it felt, we found that Bazel was probably the best match. And otherwise, I wouldn't be here. I'd be at the GNU Make conference. So we had a bunch of evaluation criteria, right? We had, it has to support iOS, and that in and of itself just, got rid of a bunch of them. Swift was another one, test, code generation, caching, dependency management. Bazel was not that great in dependency management, but we could rely on CocoaPods for doing that. Xcode integration also looked very good on paper. But, Bazel has Tulsi, and Tulsi gives you an Xcode project that just works out of the box. So what's the problem with that? And one of the criteria, or not criteria, one of the requirements that we had is we didn't want to modify the source code. We wanted developers to keep working on their source like they were used to, not require them to change anything. And this is going to be very relevant later on. Then speed. documented extensibility, et cetera, et cetera. And I'm not going to go through the full list, but Bazel was looking pretty good on paper. We read the website, we read the docs, we built a sample app, we hit some problems, we submitted some PRs, they were not accepted, we submitted some more PRs, some of them were accepted, and we managed to see a path where we were, okay, we can actually make this work. So the major problems that we thought we had were there was no easy migration path. Our apps, you'll see later, are pretty large and they have a lot of dependencies, so manually writing all the build files didn't sound like a feasible thing to do. And the major thing was the header conventions, because I'm going to explain about the headers next, but the reality is the thing that got us really excited was the build cache. All of the other stuff was like, yeah, we can also fix all of this, but the build cache sounded so promising. I took a build. We were building with Xcode at the time, and I took about, I think it was 100 or 100, a little over 100 commits, and I basically just ran them as if it was, run the first, don't clean up, and keep running, and if Xcode chokes because whatever, then just like clean up and try to keep on running them to get a sense of if we could turn every build in CI into an incremental build without actually it being incremental, what would it look like? And our back of the envelope was, we can probably cut build times by 50% if we can do this. And the build cache sounded like a really promising way of doing this. So we got all the required approvals and jumped head in and said, okay, we're not going to take the main LinkedIn app, which is probably too big. Let's take a smaller app, LinkedIn Learning. And we took that app. One of the advantages of that app is that it has a slower velocity. It has less than 20 commits per day, so it allows you to keep up if you need to do things and keep merging. It's around a little over 350,000 lines of code, around 600 tests. And the workflow that the developers were accustomed to was basically they had a pod file that specifies all of the dependencies. And the dependencies come from pod specs that get fetched by this command called pod install. And after that command runs, you essentially have what looks like a monorepo. You have downloaded all of the dependencies, you plopped them in the file system, they have like a structure inside your directory. And now you run the command line tool Xcode build, and that builds a bunch of frameworks and then writes down the app. And we said, okay, the way to do it, the way to port this app is not to write the build files manually. We're going to write a CocoaPods plugin. It has all the information in the pod files and the pod specs. We don't have to change anything. And if we end up having to revert back to Xcode, we can just do it, flip a bit, and now you build with Bazel, now you build with Xcode. We looked at the imports and said we can fix that in the Object-C library rules. Didn't look too hard. And we have one thing that our apps have, and the LinkedIn app has a lot more than the Learning app, is a bunch of mix modules where we take a lot of Objective-C and a lot of Swift, and the Swift calls the Objective-C, and the Objective-C calls Swift, and they share variables, and they live happy under the same framework, and everything is great until you try to build it with Bazel. So the other thing was the toolchain management. We wanted to manage versions of Bazel itself, and Bazel did not really provide an answer for this back then. Basilisk was around, I think, but this was before it was rewritten in Go, so it had to bring its own Python, and it had some other dependencies. So that didn't look like an option. And we also wanted to start right from the start with Bazel Remote Cache. So the new workflow was we're going to call this new plugin, and it's going to be pod Bazelize. It's going to do the same thing as pod install, except that instead of writing all of the Xcode rules for building frameworks, it's going to write build.bazel files, and then we call Bazel build, and boom, we have our app. And then we hit the mix module problem. So this was the first snag after the sweat. This is the tears part of the talk. So the mix modules are compiled by Xcode in a particular way. Essentially, when you have a mix module, you have a bunch of Swift files, you have a bunch of M files, and you have a bunch of header files. You pass all of the Swift files and the header files to the Swift C compiler, and then it generates a Swift module, and it generates a header file that's going to be used later by Clang so that you can compile the Objective-C files that might use dependencies from Swift. And then the whole thing is given to libtool, and libtool goes and packages everything into a .a. And at least that was the theory. And you'll see in a second. So we figure, OK, this is the way to do it. We're going to write an Objective-C library. We're going to put all the headers inside this Objective-C library and treat it as headers only, give it to the Swift library so that the Swift library can compile, and then pass that Swift library to another Objective-C library so that we have the end product. And the main problem with this is that now anything that depends on this is sort of a mess because it's missing that last libtool thing, so it needed like a general or something to mix it, and it started getting complicated. And this is a long way of saying, the main problem was the header import. So let me tell you how it works in the iOS world. So Xcode packages things in frameworks, and frameworks basically are directories, and they have a specific structure. So all the headers go in headers, they have modules, and they have a Swift module, they have a module map that gives you which headers are public, which come from Swift. And finally, that foo is essentially like an executable. It's like an archive. It's not executable. It's an archive of object files. The Swift module comes from Swift, obviously, and the other one is from Objective-C. But what this accomplishes in the iOS world is that in your source code, you can just, you can do two things. One is you can do @import, and we weren't too worried about supporting that one, which is a whole separate can of worms. But you can do #import, and you do foo/foo.h, and that is what they call an umbrella header. It just brings everything from the framework into the namespace, and then you can write your code. You can do #import foo bar.h when you only want a piece of that framework in your namespace. And within the framework, when you're working inside, so the first two are when you depend on a framework. The last one is when you are writing the framework itself, you can do the double quote import and just get the headers without any qualifier, And inside if you actually look at the source code for that framework, you might find that the paths don't match the ways the imports are done. You might find that the person who wrote the foo framework or the foo component, right, has a subdirectory called components or whatever, and they have a bunch of paths. So all the headers are spread everywhere. But when people use them, they use them with the framework path in the front, and within the framework, they have double quotes. So you need to do a bunch of manipulation of headers. And our choices back there was, maybe we need to write a bunch of gen rules and just like move everything to where it wants it and create the paths that it wants and then take those and pass them around. Or we could use two technologies that have been developed by the Clang team to deal with this very problem. One is header maps, which are essentially a hash map. You give it how you want the import to look when you type #import, and where the path of that file actually is in the file system. And then you pass that to Clang with a normal -i or -i quote, and then it'll read it as a hash map, and you get the imports the way you want. And the second one is VFS, which, believe it or not, the Clang compiler includes a virtual file system where you write a YAML file and you tell it, this is how I want the file system to look for this compilation, and then it goes and does. And the VFS is slower and more complicated, and they use it for dealing with the framework structure when you want to take something and pretend it looks like a framework when it doesn't. But we didn't want to go there, so we went with the header maps, which seemed a simpler approach. So we said, OK, this is what we're going to do. We're going to do header map support for Bazel. We're going to write our Bazel wrapper that manages the versions of Bazel. We're going to set up a remote cache server. We had one that kind of worked already for a different purpose. We just dust it off, set it up, we're good to go. We're going to write the CocoaPods plugin, and then we have to do a bunch of custom build rules in Starlark, but it'll be fine, right? So we did that, and then we found a bunch of problems. A lot of the things that we changed in the Objective-C headers, the Objective-C library is one of the native rules that the Bazel team is trying to get out of the core Bazel, and it's sort of intermingled with rulescc, and they're trying to get rid of rulescc from native and put it in a separate repo, so it was kind of a mess. We couldn't get any of our PRs in that section of the code there. We found that sandboxing on macOS is unbelievably slow. It's like 15 times slower than building. So if you're trying to build on macOS and you turn the sandbox off, it takes for our main app about 8 minutes without the cache. And if you turn the cache on, it takes over 2 hours. So it's not, I mean, it just basically killed all performance. We had to turn that off. And we had, I think this has been fixed now, but this cache didn't used to play well with remote HTTP cache. If you had one, you couldn't have the other. I believe this has been fixed now, but on top of that, this cache also has a problem that it does no space management, and we wanted to run it on developers' machines, so we didn't want to just let it fill until we get, calls from IT going like, why is this thing taking so many gigabytes? And we also found an interesting behavior, which was when we were using the remote cache, when Bazel was pretty much done with the build, there were still a bunch of artifacts that it needed to upload in the final phases, and it wasn't done until all of those were uploaded. So it was still taking time to do that final upload, and it was also affecting performance. So we came up with a bunch of solutions for that. The first one is, rather than building the header maps into Bazel itself, we found in the Clang compiler there's a Python script that's called hmap-tool that basically can take a JSON file and generate the format that the Clang compiler wants for header maps. So we put that in a bunch of gen rules. Then we wrote that CocoaPods basalizer that I talked about, and we had to write some rules to handle the modules. We turned sandboxing off, just, don't even bother. Look, no sandbox. And then the Bazel wrapper. This part is kind of interesting. We built into the Bazel wrapper a way to run a distributed Bazel remote cache. And the way that works is Bazel wrapper does the toolchain management. So it'll look at this JSON file that I was talking about and figure out which version of Bazel you want to use. And then it'll go and fetch that version of Bazel and execute it. But on top of that, it'll also look at the environment in which you're running, and it'll see if there's a Bazel remote running in that machine locally as a daemon. And if there is none, then it'll spin one up. It'll go and fetch the latest version from a given location. We built it both ways. It can do either GitHub or it can do some other location. And it'll fetch the latest version, it'll run it, let it bind to an ephemeral port, and put the address in a socket so that then later Bazel wrapper can read that address and wire it up into the Bazel command line, so you get an automatic cache. And then Bazel remote can function as a primary cache with space management and all of that, and linger and keep moving all of those artifacts to the main central cache. And then if it's been idle for like, I think half an hour, configurable, of course, then it'll just kill itself. And the whole thing starts again. And that solved a bunch of the Bazel remote problems. It also had another interesting effect, which was even for machines that were a little configured a little differently that we found when we were debugging the cache. We found, for instance, that some of the machines on our CI, and this is probably also because we turned the sandbox off, some of the machines had the command line tools installed, and then when Clang wrapper was compiled, it was linked with a certain version of libc, and then on other machines that didn't have command line tools installed, Clang wrapper will get linked with a different version of libc, and then of course you get 0 cache hits because Clang wrapper is sitting at the bottom of the dependency chain, except that when we did this Bazel remote thing, then you get some caching, because even if the machines are slightly differently configured, they are self-consistent. So you get some benefits from caching, even in the worst case. You bloat the cache because now you have twice all the artifacts in the centralized cache, but space is cheap. So that's what it looks like when you run Bazel wrapper. We called it Bazel, so people don't have to think about it. They just run Bazel build. And then there's a couple of lines there that are not normal Bazel. Found Bazel remote here, is listening in that port, using it, and which version of Bazel you're running. And it's pretty transparent, works great, people love it. Nobody uses it but the build tools engineers, so we love it. And we Bazelized the first LinkedIn app, which was the LinkedIn Learning. And what you see there is we were running CI with both. So we took 2 machines for Xcode builds, test and release, and we took 2 machines for Bazel builds, test and release. And you'll notice that the Bazel builds without the cache were running slower than the Xcode builds that have no cache. And then we turned the cache on, and the times dropped, and they flipped. It's also quite interesting that they flipped, because the test release, when you're building a release is slower because you have to run all the optimizations in the compiler and all this stuff. And building a debug version is faster, and even with the test, it was still faster. But when we added the cache, then the release build was mostly cache, but you still had to run the tests. So then they flipped. But we had a pretty good success with this app. And then we tried to do the LinkedIn app, which is the bigger app. That one is about, it takes about 50 plus commits per day. It's about 2 million lines of code, and it's mixed Swift and Objective-C, 40% Objective-C, 60% Swift. And it has around 6,500, a little over 6,500 tests. And when we tried to port that app, then we found that that Python script that we had found in the Clang repo was definitely too slow for building that app. It had just way too many headers. We hit very subtle compilation problems because of the way we were compiling, where Xcode was not. When we were calling Swift and Clang, it wasn't finding what it was expecting. And we found some Swift compiler bugs. For instance, the testable imports, we found that if you, depending on how it found the frameworks, it could find a framework transitively, and sorry, not the framework, the modules. It could find a module transitively and import it as a transitive dependency of a different module. And then when you did a transitive, testable import of that same module, then the Swift compiler will say, oh, it's already imported, I don't have to do anything. But it was not imported in a testable way, so then none of the symbols that you actually wanted to test were there. So that was a problem. So we did the take 2. We fixed a bunch of these problems. We rewrote the header map generation in C. And the header map format is pretty amenable to just, you mmap it. It's super efficient if it's low level. If it's Python, it's not that efficient, and we found that the hard way. Talk about failure. Then we got some faster machines for the build cache, because we were having also performance problems. Turns out that Bazel pounds on the remote cache pretty hard. And we rewrote all of our rules to create actual frameworks. And that was actually a brilliant stroke by one of our build engineers that said, let's just give it what it wants. Like, Xcode wants to build it this way, and it's used to building it this way. And if we just build it in exactly the same way, we're going to avoid all of these problems. And that worked wonderful. And so we wrote these new framework rules where before we were just trying to manage the libraries. Keith from Lyft talked about this a little. Like, Bazel has this concept of building rules and packaging rules. And they're very different, because the packaging rules are terminals. You can't depend on them. They're just to produce something in a certain shape. And then the build rules are the things that have providers that you can propagate. And what we did is we said, no, we're going to build this packaging rule that is also a build rule, and you can depend on it. And it's just going to pass the right providers so that other things can look at the headers and can look at the build things and the configurations and all that stuff. And that worked really well. It just solved a bunch of compilation problems. You have no idea. And so we finally did the LinkedIn app. And by now, we had a build cache fully functioning and running. So when we turn it on, you can see the spike where it's doing more work than Xcode, because it's both building and filling the cache. It has to fill, it has all the misses, and then it has to fill it in. But then it starts stabilizing, and it starts dropping down. And Xcode is 25 minutes climbing to 30. And we have in some cases less than 5-minute builds, because it's when people probably didn't change anything and it was completely fully cached. And then we have a little less than that, like 20, 15 minutes when it actually has to build stuff. And this is without breaking up the app or trying to make it more parallelizable or anything like that. If you just take the app right now and just build it with Xcode, and then you build it again with Bazel without the cache, and then you build it again with Bazel, but now with the cache. Those are the timings. So this is not the common scenario because usually people change stuff, so there's some amount of rebuilding. So this is the best case for the cached times. But you'd be surprised how many times people change things that don't trigger any rebuilding at all. Images or translation, things like that tend to not require code recompilation. And so what lessons did we learn? Our back of the envelope was right. We had about a 50% build time decrease. And Bazel's external dependencies were really hard to manage. We still don't have a great answer. I was super interested in what the workspace story was because we run the CI without access to the internet, and finding out what Bazel wants to download from the rules, especially when they have maybe downloaded, maybe not, you're never sure. And overall, the experience of taking it and moving it, it's kind of funny because Keith from Swift was saying that he was of the opinion of contributing all of this stuff back and being on the bleeding edge, and he didn't think that other people being on the bleeding edge will save him any work because they were probably using it in a different way. And for us, it was completely the opposite because every time we'd hit a bug, Kit had already fixed it. So we were like, oh, okay, so he's on the bleeding edge. We can hang back, a few releases, and then by the time we get to that release, they've hit all the bugs. So for us, it was the opposite. I'm glad that my talk came second. And what would have helped? So Bazel looked really good on paper, and it looked much better on paper than it was in reality. The docs are great until they are not. And then we ended up having to read a bunch of source code, and we ended up finding a bunch of places where the docs said one thing and the source code said some other thing. The Objective-C support, it's definitely not great and not easy to change, and it's not, we had a bunch of cases where for instance, things that we were depending on, there was recently some Objective-C rework, which I think was a great thing actually. I think it moved it in the right direction, but it was super disruptive. Like we had to rewrite all of our rules, and it took us a while to fix that. And the sandboxing, if there was one thing where that I wish was much better was the sandboxing, because if you're just building, turning the sandboxing off, it's actually not that big of a deal. But if you're writing rules, then yeah, you want that sandboxing on because you don't know what you're doing. And if it takes 2 hours to do a full run and you keep hitting problems and you change the rules and then you're not sure that you didn't break something else, so you have to clean everything up and start it again, then it gets pretty old pretty fast to work that way. And it's not sandbox exec. I actually looked into that. So we have it on our to-do list to try and figure out what's wrong with the sandboxing. So that's where we are. We're shipping from Bazel built app. So if you have the LinkedIn app on your phones, then you have a Bazel built LinkedIn app. We don't have a good solution yet for the local builds, so we're looking into that. We have some ideas, and we've talked to a bunch of other people who have iOS apps, so that's next on our roadmap. We're also looking at remote execution, which is very unclear to us if it's going to help because of the sandboxing problem, and it requires having the sandboxing actually working. But we're doing some experiments to see what it looks like. And we have discussed open sourcing all of this stuff, Bazel wrapper. We have a bunch of changes to Bazel remote that might or might not be of interest, especially if you don't have Bazel wrapper to go with it. And that's pretty much it. So thank you.
Thank you, Oscar. As before, I know it's late and I don't want to keep you from the reception, but I think if you have any questions, The mics in the middle could be good. Give folks a few seconds to get up there. John, why don't you kick it off?
John Field from Google. I believe if I read that correctly, you said a clean build using Bazel was without caching was faster than Xcode on a clean build. Is that correct?
Yes, it is correct.
That's not obvious. It's not obvious to me that should necessarily be the case. Do you have any insight into that?
Yeah, I think it's because we have. I need to qualify that with something. We're still using Xcode ships with two different build systems. It ships with a legacy build system, and it ships with a newer build system that's supposed to be faster and shinier, and it's never worked for us. So we are still using the legacy build system. And one problem the legacy build system has is that it tracks dependencies at a much coarser level. So if you have a framework, it'll go and say this new framework depends on this framework, so let's wait until it's built. And by it's built, it means compile and linked before it starts building the other framework. Whereas Bazel will say, oh, look, headers, that's all I need, right? And start eagerly compiling other stuff, so it parallelizes much better. So I suspect that is the reason why Bazel is faster.
All right, thanks.
Hey, I'm Robin Abel from Improbable in London. I had a quick question. Your graphs are basically saying that sandboxing is extremely expensive.
Yes.
But I was wondering, have you tried enabling sandboxing with caching? And is that, what is the performance relative to Xcode?
Sandboxing, we have played with sandboxing with caching, and I don't have the numbers with me. It's of course faster than sandboxing without caching, and it's not as fast as caching with no sandboxing. So we essentially went for speed of builds rather than safety, living on the edge and all that. But yeah, I don't have the numbers, but it's in between, essentially.
Okay, thanks.
Hi, I'm Ed from Bloomberg. So you talked about, obviously, iOS for all of this talk. Are you also responsible for the Android build, or is that a separate?
No, there's a separate team that deals with Android, and they seem to be really happy with Gradle, so we don't want to touch something that's not broken. Oh, sorry, up there, yeah.
Just a quick question. You mentioned one of the things you were, Anthony from Twitter. So you were mentioning one of the things that you were kind of thinking about is first off, acquiring more machines, just for a sense of scale. How many machines do you guys currently use for your CI process?
How many machines do we use per? So how many machines we use per?
Just in the fleet.
In the fleet, there's thousands of them. I know it's more than 1,000 and probably less than 2,000.
Okay, Mac.
I don't know.
Okay.
It's thousands of them, but they're different. There's also, we're moving the CI pipeline to the newer minis. That was one of the things that made a huge difference, not just with the build time, but with the everything time. Mm-hmm. When we deployed the new minis, our build times just drop, and people were like, "Ooh, did you do the Bazel thing?" And we're like, "Nah, we just we should have said yes, but we just said no. That's the new hardware." And then the Bazel drop didn't look that great in comparison, just because of the hardware. But it was because the old hardware was so bad. And Bazel actually was much better in the new machines because they have more cores, and Bazel can actually use them.
Awesome, thank you.
No problem. Yeah.
Hi, I'm Alex from Google. We actually are trying to investigate what's going on with sandboxing, because some users are reporting that in some cases it's pretty terrible on Mac, and it seems to be dependent both on the macOS version.
Yes.
The hardware, like iMac Pro versus MacBook versus whatever else, whether you're using Swift or Objective-C, and we currently aren't really sure where to go on because there is not enough data points. But the behavior is vastly different for different users depending on what exactly they're building. So if you have more data to contribute, you or anyone else in the room, search for the issue on GitHub, please.
We should absolutely talk. It's we've done a bunch of experiments. I was convinced that it was SandboxFS. I filed a PR, not a PR, an issue. You've seen it where when I upgrade, I have one iMac that I keep on the latest version, and I was in a Catalina beta, and the build was taking 22 hours. So it was ridiculously slow, and I was trying to figure out what it was, and I rewrote. I mean, I didn't rewrite. I took Sandbox FS out of the equation. I just wrote my own Sandbox FS command in C that didn't do any sandboxing, just exected, and it was just as slow. So I think it's got to be something with the file system, APFS, or the way it does the symlinks, or there is something there that is definitely not right. And yeah, well, we shall definitely talk. I'd be happy to help with data or running things, whatever.
And the last one,
here.
cool. Eric Mavernick, Microsoft. 2 months ago at the London Build Meetup, there was a presentation by one of our devs from BuildXL, Microsoft Build Accelerator. There's support in BuildXL for about 10, maybe 15% consistent reduction in performance, like overhead for sandboxing in BuildXL side for Mac. The presentation was on the new Catalina driver support that we're adding in the BuildXL open source code base. So. For yourself and for the Google folks working on this, you might want to take a look. The presentation from London Build Meetup on, I think it was October 1st. Contact me. You'll see the BuildXL link tomorrow after my talk in the morning. But it might be a good way to do a drop-in replacement if it's compatible with your sandboxing approach. So
Definitely. Thank you. Yeah, we also tried Sandbox FS from the Bazel build, and it was not as bad, but it was not great because fuse in the middle, and every time you do a syscall in fuse, it's like 4 syscalls or whatever, so it's not great. But yeah, I'll look that up. Thank you.
Okay, well, this is great. I really appreciate it. Appreciate you coming out. Appreciate everybody sticking around. Right after this, I mean, probably right now, there's a reception, and I hope everybody can join us. And thanks for coming.
Thanks to you. Thank you.
Thanks. See you tomorrow.
So, no.
Same time, same place.